Welcome to Week 2 of Business Forecasting. This time we shall discuss Chapter 2, which is about time series graphics. A good starting point for any data analysis is to visualize the data first. Creating graphs allows you to quickly spot important characteristics such as trends, patterns, outliers, changes over time, and how different variables relate to each other. These visual insights are not just for observation. They should guide how you choose and design your forecasting methods. In other words, the nature of the data influences both the type of graph you create and the forecasting technique you apply. However, before generating these visualizations, the data, especially time-based data, must first be properly organized, such as structuring it as a time series in R. Example: imagine you are tracking your monthly electricity bill over the past 2 years. If you simply look at the numbers in a table, it may be hard to notice anything meaningful. But once you plot the data on a graph, you might clearly see that your bills spike every summer due to air conditioning use. You may also notice a gradual increase over time because of rising energy costs. From this graph, you can conclude two things. There is a seasonal pattern, higher bills in summer. There is a trend, costs slowly increasing over time. Because of these patterns, you would choose a forecasting method that accounts for both trend and seasonality rather than a simple average. This shows how plotting the data first helps you make better and more accurate forecasting decisions. A time series can be understood as a sequence of numerical observations recorded over time, together with information about when each observation occurred. In R, this type of data is organized using a T-Symbol object, which is essentially an enhanced data frame that incorporates a clear time-based structure. At the center of this structure is the index variable, which represents the time component, such as year, month, or day, and links each data value to a specific point in time. Depending on how frequently the data is collected, different time formats or functions are used to properly define this index, ensuring that the temporal aspect of the data is accurately represented. In addition to the index, Symbol objects also allow the inclusion of key variables, which make it possible to store multiple related time series within a single dataset. These key variables act as identifiers that distinguish different groups or categories, such as locations, product types, or demographic groups, while still maintaining a unified structure. This organization is particularly useful because it allows analysts to work with complex data sets efficiently while preserving the relationships between different time-based observations. Once the data is structured as a T-Symbol, it becomes much easier to manipulate and analyze. Common data operations, such as filtering specific rows, selecting relevant variables, summarizing totals, or creating new computed fields, can be applied seamlessly while preserving the time structure. This ensures that the dataset remains consistent and ready for further analysis, visualization, and forecasting. To make this more concrete, consider a simple example of a small cafe tracking its daily coffee sales. Each day's sales figure is paired with the date it was recorded, making the date the index variable and the sales figures the observed values. If the cafe has 2 branches, an additional variable identifying each branch can serve as a key, allowing both branches' sales data to be stored in the same dataset while still being distinguishable. With this structure in place, the cafe owner can easily analyze patterns, such as identifying higher sales on weekends or observing gradual growth over time. Because the data is properly organized as a time series, it becomes straightforward to detect trends and seasonal patterns, which can then be used to make informed forecasts about future sales. Now let's talk about time plot. A natural and essential way to begin analyzing time series data is by creating a time plot. In this type of graph, the observed values are plotted against time, and consecutive data points are connected with straight lines to show how the values evolve over a period. This kind of visualization is especially useful because it immediately reveals patterns, trends, and unusual behaviors in the data. In R, a common tool used for this purpose is the autoplot function, which automatically detects when the data is a time series and generates an appropriate time-based graph without requiring complex setup. When a time plot is created, it often uncovers important features that may not be obvious from raw data alone. For example, a dataset on airline passenger loads might show periods where no passengers were recorded due to external events such as labor strikes. It may also reveal sudden increases or decreases in demand caused by operational changes, as well as recurring patterns like dips during holiday seasons. Additionally, long-term fluctuations or cycles in the data may become visible, such as periods of growth followed by decline and then recovery. All of these patterns are critical because any forecasting model must take them into account to produce accurate predictions. Ignoring these features would lead to misleading or inaccurate forecasts. In simpler time series, time plots can clearly display both trend and seasonality. A trend refers to the general direction in which the data is moving over time, whether it is increasing, decreasing, or remaining stable. Seasonality, on the other hand, refers to repeating patterns that occur at regular intervals, such as monthly or yearly cycles. For instance, in a data set of monthly drug sales, a time plot might show a steady upward trend combined with recurring spikes or drops at specific times of the year. These patterns may be influenced by external factors such as government policies, pricing structures, or consumer behavior. To illustrate this in a simple and relatable way, imagine tracking your monthly grocery expenses over several years. When you plot the data on a time graph, you might notice that your expenses gradually increase over time due to inflation. This is the trend. At the same time, you may observe that your spending spikes every December because of holiday celebrations and drops sharply in January after you cut back on spending. This is seasonality. You might also see occasional unusual spikes, such as during a large family gathering or special event. By looking at this time plot, you can clearly understand your spending habits and predict future expenses more accurately. This demonstrates how time plots not only make data easier to interpret, but also serve as a foundation for building effective forecasting models. After time plot, let us now discuss time series patterns. When analyzing time series data, it is important to clearly understand the different types of patterns that may appear, particularly trend, seasonality, and cyclic behavior. These terms are often used casually, but each has a specific meaning that helps guide how we interpret data and choose appropriate forecasting methods. A trend refers to the long-term direction of the data, indicating whether values are generally increasing, decreasing, or changing direction over time. This movement does not have to follow a straight line. It can curve upward or downward, and sometimes it may even reverse direction, from growth to decline or vice versa. For example, if you track your monthly income over several years, you may notice that it gradually increases as you get promotions or better opportunities. That steady upward movement represents a trend. A seasonal pattern, on the other hand, occurs when data follows a regular and repeating pattern tied to a fixed calendar period, such as days, months, or quarters. Seasonality is predictable and happens at consistent intervals. For instance, retail sales often increase every December due to holiday shopping and drop in January after the holiday season ends. This repeating yearly pattern is a classic example of seasonality. It is important to note that some datasets can have more than one seasonal pattern. For example, daily sales data may show both weekly patterns, weekends versus weekdays, and yearly patterns, holiday seasons. In contrast, a cyclic pattern involves rises and falls in the data that do not occur at fixed or predictable intervals. These fluctuations are usually influenced by broader factors such as economic conditions, political events, or market dynamics. Cycles tend to last longer, often several years, and their timing and magnitude can vary. A good example is the housing market, where prices may rise during economic booms and fall during recessions, but the exact timing and duration of these cycles are not consistent. This is what distinguishes cycles from seasonality. Seasonal patterns are regular and calendar-based, while cycles are irregular and influenced by external forces. Many real-world time series contain a combination of these patterns, making analysis more complex but also more informative. For example, consider a business tracking its monthly sales over 10 years. The data might show an overall upward trend as the company grows, seasonal spikes every December due to holiday demand, and occasional downturns during economic recessions. To accurately forecast future sales, any chosen model must be capable of capturing all these elements: trend, seasonality, and cycles. To make this easier to understand, imagine you are analyzing your gym attendance over several years. You might notice a steady increase in attendance as you become more committed to fitness, trend. At the same time, attendance might spike every January due to New Year's resolutions and drop during holidays like December, seasonality. Additionally, there may be irregular periods where attendance drops for several months due to work stress or life changes, cyclic behavior. By identifying these different patterns, you gain a clear understanding of your habits and can better predict future behavior. From time plot, let's tackle another factor in time series, which is the seasonal plot. A seasonal plot is a specialized type of graph used in time series analysis that focuses on highlighting patterns that repeat over regular time intervals, such as months, quarters, or days of the week. Unlike a standard time plot, where data is displayed continuously over time, a seasonal plot groups the data by season, for example, months in a year, and overlays multiple years on the same graph. This makes it much easier to see recurring patterns and compare how those patterns behave across different years. In R, this can be done using functions like gg_season parenthesis, which automatically organizes the data into seasonal groupings for visualization. One of the key advantages of a seasonal plot is that it allows patterns to stand out more clearly than in a regular time plot. For example, when examining monthly drug sales data, a seasonal plot can reveal consistent spikes or drops that occur at the same time each year. Because all years are layered on top of each other, it becomes easy to identify whether a pattern is stable or if certain years behave differently. This also helps in spotting unusual events or anomalies, such as a sudden drop or increase that does not follow the usual seasonal pattern. For instance, in the case of anti-diabetic drug sales, a seasonal plot shows a noticeable spike every January. This is likely due to consumers purchasing medications in advance at the end of the year, with the sales being recorded slightly later. At the same time, the plot may reveal unusual observations, such as a lower than expected number of sales in a particular month, which could be due to data collection issues or external disruptions. These insights are much easier to detect when the data is visualized seasonally rather than chronologically. In some cases, data may exhibit multiple seasonal patterns, meaning that patterns repeat at more than one frequency. For example, electricity demand data recorded every 30 minutes may show daily patterns, higher usage during the day and lower at night, weekly patterns, different usage on weekdays versus weekends, and yearly patterns, higher demand in summer or winter. Seasonal plots can be adjusted to focus on any of these cycles by specifying the desired period, allowing analysts to isolate and study each pattern separately. To make this concept more relatable, imagine you are analyzing your daily study hours over several years. If you create a seasonal plot based on the days of the week, you might notice that you consistently study more on weekdays and less on weekends. If you instead group the data by months, you might see that your study time increases during exam months and decreases during vacation periods. By overlaying multiple years, you can also identify unusual periods, such as a semester where your study time dropped significantly due to personal circumstances. This demonstrates how seasonal plots help uncover repeating patterns and deviations, making them an essential tool for understanding time-based behavior and improving forecasting accuracy. If we have seasonal plots, we also have seasonal subseries plots. A seasonal subseries plot is another way of visualizing time series data that highlights seasonal patterns even more clearly, than a standard seasonal plot. Instead of overlaying all years on a single graph, this method separates the data into smaller mini time plots, with each panel representing a specific season, such as a month or quarter. Within each mini plot, the data is displayed over time, allowing you to see how that particular season behaves across different years. A key feature of this plot is the inclusion of horizontal lines that represent the average value for each season, making it easier to compare whether certain months or quarters are consistently higher or lower than others. This type of visualization is especially useful because it not only shows the overall seasonal pattern, but also reveals how that pattern changes over time. For example, it can help identify whether a specific month is becoming more important or less significant as years go by. While some datasets may not show dramatic differences in this format, in many cases, seasonal subseries plots are one of the most effective tools for detecting subtle shifts within particular seasons that might otherwise go unnoticed. A good illustration of this can be seen in tourism data, where the number of holiday trips varies by location and time of year. When analyzing such data, standard time plots may show general seasonal patterns, but they may not clearly indicate when peaks occur in different regions. Seasonal plots can help reveal these timing differences, for instance, showing that some regions experience peak tourism in summer, while others peak during cooler or drier months. However, when using seasonal subseries plots, it becomes even easier to observe how tourism in each specific quarter changes over time for each region. This allows analysts to detect trends such as sudden increases in tourism in certain areas or changes in travel behavior during specific times of the year. To make this concept easier to understand, imagine you are tracking your monthly savings over several years. A seasonal subseries plot would separate your data into 12 mini charts, one for each month, January, February, and so on. In each chart, you would see how your savings for that specific month change year after year. You might notice that your December savings are consistently low because of holiday spending, while your January savings are higher as you try to recover financially. Over time, you may also observe that your savings in certain months are improving due to better budgeting habits. This kind of visualization helps you clearly see both the recurring seasonal patterns and how your financial behavior evolves over time, making it easier to plan and forecast future savings. Another one is the scatter plot. A scatter plot is a useful graphical tool for examining the relationship between two variables in a time series dataset. While earlier graphs like time plots focus on how a single variable changes over time, scatter plots allow us to compare two variables directly by plotting one on the horizontal axis and the other on the vertical axis. This makes it easier to see whether the variables are related and how they influence each other. For example, when electricity demand and temperature are plotted against each other, the scatter plot reveals that demand tends to increase when temperatures are very high due to the use of air conditioning, and also when temperatures are very low due to heating needs. To quantify the strength of the relationship between two variables, we often compute a correlation coefficient, which measures how closely the variables move together in a linear way. This value ranges from 1 to 1, where values close to 1 indicate a strong positive relationship, both variables increase together. Values close to 1 indicate a strong negative relationship, one increases while the other decreases, and values near 0 suggest little to no linear relationship. However, it is important to understand that correlation only captures linear relationships and can sometimes be misleading. For instance, two variables may have a strong, curved, or nonlinear relationship that the correlation coefficient fails to fully capture, making it essential to always examine the scatter plot itself rather than relying solely on numerical values. Another important insight is that datasets can have the same correlation value but very different patterns when plotted. This highlights why visualization is critical in data analysis. A single number cannot fully describe the complexity of relationships in data, whereas a graph can reveal clusters, outliers, or unusual structures that might otherwise be overlooked. When dealing with multiple variables, analysts often use a scatterplot matrix, which displays all possible pairwise relationships between variables in a single grid of plots. Each panel shows the relationship between two variables, allowing for a quick and comprehensive overview of how all variables interact with each other. This approach is especially helpful in identifying which variables are strongly related and which are not, as well as spotting patterns across different groups or regions. To make this easier to understand, imagine you are studying the relationship between your daily study time and your exam scores. If you create a scatter plot with study hours on the horizontal axis and exam scores on the vertical axis, you might notice that higher study hours generally correspond to higher scores, indicating a positive relationship. However, you may also observe that beyond a certain point, studying more does not significantly improve scores, suggesting a non-linear relationship. If you also include other variables, such as sleep hours, stress levels, and class attendance, you could use a scatterplot matrix to explore how each of these factors relates to one another. This would give you a more complete picture of what influences your academic performance and help you make better decisions moving forward. And we have the lag plot, which is a useful tool in time series analysis that helps reveal patterns in data by comparing current values with past values. Instead of plotting one variable against another different variable, a lag plot compares a variable with itself at earlier time periods. In this type of graph, the current observation at time t is plotted against a previous observation at time tk, where k represents the lag. By creating several lag plots with different values of k, we can better understand how past values influence present behavior and whether patterns such as seasonality exist. Lag plots are particularly helpful in identifying seasonal patterns and correlations over time. For example, in quarterly beer production data, strong positive relationships appear at lags of 4 and 8. This means that the production level in a given quarter is very similar to the production level in the same quarter of previous years, clearly indicating a yearly seasonal pattern. On the other hand, negative relationships may appear at certain lags, such as lag 2 or 6, where high values, peaks, are compared with low values, troughs. This happens because different parts of the seasonal cycle are being compared. For instance, a high production quarter being plotted against a low production quarter. What makes lag plots powerful is that they visually show whether the data is related to its past values. If the points form a clear pattern or line, it suggests a strong relationship between past and present values. If the points are scattered randomly, it indicates little or no relationship, meaning the data may be more unpredictable. This insight is very important when selecting forecasting models, as many models rely on the idea that past values influence future outcomes. To make this easier to understand, imagine you are tracking your monthly savings over several years. If you create a lag plot comparing this month's savings with the savings from 12 months ago, lag 12, you might notice a strong pattern where the values are very similar. This would suggest that your savings behavior follows a yearly cycle. For example, saving more at the start of the year and less during the holiday season. However, if you compare this month's savings with the savings from 6 months ago, lag 6, you might see an opposite relationship, high savings compared with low savings, because mid-year expenses differ from end-of-year spending. This simple example shows how lag plots help uncover repeating patterns and relationships within the same dataset, making them a valuable tool for understanding and forecasting time series data. Let's also discuss autocorrelation. This is a concept used in time series analysis to measure how strongly a variable is related to its own past values. While ordinary correlation examines the relationship between two different variables, autocorrelation focuses on how a single variable relates to itself at different points in time. In other words, it tells us whether past values of a time series can help explain its current behavior. Each autocorrelation coefficient corresponds to a specific lag. For example, the first autocorrelation, R1, measures the relationship between the current value and the value from one time period earlier, while R2 compares the current value with the value 2 periods earlier, and so on. All of these coefficients together form what is known as the autocorrelation function, ACF, which provides a summary of how the data is correlated across different time lags. The ACF is often visualized using a graph called a correlogram, where the lag values are plotted on the horizontal axis and the autocorrelation coefficients on the vertical axis. This plot helps us see how the strength of the relationship changes as we look further back in time. For example, in quarterly beer production data, the ACF shows a strong positive value at lag 4, meaning that production levels tend to be similar from one year to the next, since 4 quarters make up a year. At the same time, there are strong negative correlations at lag 2, indicating that high production periods are often followed by lower production periods halfway through the year. These patterns clearly reflect the seasonal nature of the data. Autocorrelation plots are especially useful for identifying trend and seasonality in time series data. When a dataset has a trend, the autocorrelation values for smaller lags are usually large and positive because values that are close in time are also similar in magnitude. As the lag increases, these correlations tend to gradually decrease. On the other hand, when the data contains seasonality, the ACF will show repeated spikes at regular intervals corresponding to the seasonal period. For instance, in monthly data with yearly seasonality, strong correlations would appear at lags of 12, 24, and so on. When both trend and seasonality are present, the ACF combines these features, often showing a slow decline along with a repeating wave-like or scalloped pattern. To better understand this, imagine you are tracking your monthly expenses over several years. If your expenses gradually increase due to inflation, then months that are close together, such as January and February, will have similar values, resulting in high autocorrelation at small lags. This reflects a trend. At the same time, if your expenses spike every December due to holiday spending, you will see strong autocorrelation at lag 12. Since each December resembles the previous one, this reflects seasonality. By examining the ACF, you can clearly see both patterns and use this information to choose a forecasting model that accurately captures how your expenses behave over time. The last topic in time series is white noise, which refers to a type of time series data that has no clear pattern, no trend, and no relationship between its values over time. In other words, each observation is completely random and independent of the others. Unlike most real-world data, where past values often influence future values, a white noise series behaves unpredictably. Knowing what happened before gives you no useful information about what will happen next. This lack of structure means that white noise has no autocorrelation, or in simpler terms, the values do not show any consistent relationship with their past values. When we examine a white noise series using an autocorrelation function, ACF plot, we expect all the autocorrelation values to be very close to 0. Because the data is random, there may still be small fluctuations, but these are due to chance rather than any real pattern. To help determine whether these fluctuations are meaningful, we use statistical bounds, typically shown as horizontal dashed lines on the ACF plot. For most white noise data, about 95% of the autocorrelation values should fall within these bounds, which are calculated as plus 1.96 divided by the square root of the number of observations. If the values stay within these limits, it confirms that the data is essentially random and does not exhibit any significant structure. The key implication of identifying white noise is that such data cannot be reliably forecasted. Since there are no patterns, trends, or relationships to model, any attempt to predict future values will be no better than random guessing. This is why recognizing white noise is important. It tells us that more complex forecasting methods will not provide meaningful improvements. To make this concept easy to understand, imagine you are recording the outcome of flipping a fair coin 50 times. Each result, heads or tails, is completely independent of the previous flips. Even if you observe several heads in a row, it does not increase or decrease the probability of getting heads on the next flip. If you plot these results over time, the pattern will appear random, and any attempt to predict the next outcome based on previous ones would be unreliable. This is exactly how a white noise time series behaves, purely random with no predictable structure, making forecasting essentially impossible. That wraps up week 2. Thank you and see you next week.